Hello, and welcome to the development-focused devlog for Look Left Studio. I'd like to introduce you to some of the Netcode solutions that Rogue Royale has gone through, and talk about some of our ongoing work. Multiplayer games need some way for local clients, you, to play games with remote clients, other players, while keeping everything synced. In an ideal world, when you move in your game, other players see the same movement at the same time. But we have this nasty stuff to deal with called latency, where it takes time for information to travel over the internet. One solution is the client-server model with lag compensation. With lag compensation, we have clients locally predicting their states with an authoritative server keeping everything synced. Lag compensation is the tried and true netcode supported by almost all first-person shooters. Your local client predicts the position of your character while showing you the past positions of all other characters, and an authoritative server dictates all the gameplay logic. Some great references for lag compensation from Overwatch and Valorant can be found in the video description. Let's break it down. Your local client will predict your character's position and send inputs to the server to process. These inputs enter a server buffer and are executed on a later frame to prevent dropped inputs. The server then runs the simulation and sends the results back to your client and all other players. Other clients will buffer this world state, then on a future frame, the movement is shown. This avoids any jitter. With each client seeing different states of the world, the authoritative server knows how each client views the world and is responsible for all hit detection and gameplay logic. Another approach is Rollback, which is a form of netcode commonly adopted by fighting games because it doesn't show you the past position of other players. Instead, it tries to keep all clients synced at the same frame by predicting player inputs and deterministically updating all objects each frame. If there is a misprediction for player inputs, the client can roll back to a previous state and resimulate the world back to the current frame. Let's break it down step by step. A constant stream of inputs will be sent between clients, but because client B doesn't have the movement input yet, client B doesn't move character A. When client B gets the input and checks that against their predicted one, the mismatch is detected. Client B rolls back to frame 0, then resimulates with the correct input. This process continues throughout the duration of the game, relying on determinism for the clients to remain synced. The major downside to this approach is that you have to be able to simulate multiple frames at once, so performance is critical. Also, more players means more mismatches. Another approach is a hybrid authoritative server with rollback prediction and correction. Clients send their inputs to other clients, but also to a server that runs an authoritative simulation. The server then sends the world states back to the clients, just like the client-server model. This allows us to have rollback predictions on all characters, but drops the requirement for determinism and simulating the entire world at once. Let's break it down. Your client will send inputs to both the server and other clients. The server will then buffer and execute those inputs, just like we saw before. Other clients will run rollback prediction and correction using your inputs, keeping the states between clients as synced as possible. The server sends a constant stream of world states out to the clients, and the clients verify that their history matches the authoritative one. If so, you continue. If not, the client rolls back and a reprediction occurs. The hybrid rollback with an authoritative server is an interesting approach, and one that we are working with now for Rogue Royale. The exciting thing is that we no longer have to send all inputs and data to all clients. This way, we can support a larger player count, since clients don't have to simulate the entire world at once. Given a scenario with 3 clients that are spread out, the server can decide what information each client needs to know about. Then, during a world state update, the server only has to send clients the information for the world around them. Client A only needs to know about itself and Client B. Client B needs information on all 3 players, and Client C only needs information for itself and B. This can also simplify inputs, because clients only need to send inputs to the players that the server says it needs to know about, which leads to less mispredictions. So with our netcode solution picked out, we get to last sprint's work, component creation and prediction. In an attempt to have a modular approach to character creation, I've created netcode components that are synced between the client and the server. Let's go over the creation and tracking of a knockback component. On a given frame, one client can hit another, causing a knockback component to be generated and attached to the hit character. This component is tracked via a class ID and an instance ID. This keeps the components synced between clients and the server. When a world state is sent to clients, the world state contains the frame and all components that were updated on that frame. Just looking at the knockback component, we see that it was updated on frame 7 and tracked with its class ID, unique instance ID, and the owner entity. This data then gets sent off to all the clients that need to know about it. The issue with this occurs with client predictions. The client will predict the creation of a knockback component, but because they don't see the whole world like the server does, they cannot assign it a unique instance ID. Instead, the client just creates a predicted component and simulates the results like normal. Later, the server will generate a knockback component on the same frame and send that component over to the clients. Once it arrives, the client rolls back to the server frame from the packet, deletes all predicted components, and resimulates with the newly synced server component. Because the end result is generally the same, this doesn't produce any visual jitter for the clients. One potential route we could have gone to solve this problem is to have a hard requirement of only one instance of each component type per entity. This way, it becomes trivial to track components between the client and the server. It's certainly a solution we will consider if performance becomes an issue, but for now it's nice to have multiple of the same type of component. Anywho, it's time for me to be done with devlogs and get back to some game development. If you're interested in following along, or want to chat about game dev, check out our Discord through the link in the description. Thanks for watching. I'm excited to see where the next 2 weeks of development go.